Hi everyone, this is just a quick video about the diagrams that are used to represent waves in closed air columns and open air columns that I thought I should put out just to clear out some misconceptions and confusions. Okay, so just quickly going over some of the terminology that we've already covered. Um, Atmospheric pressure is got some value. I haven't spoken about it before because it's beyond the scope of the syllabus, but what it generally talks about is the amount of force in newtons that is spread over some particular area. So here we got a whole heap of molecules in our atmospheres that make up um, the gases that our atmosphere is made out of. Now, they are being pulled towards the center of the Earth by the Earth's gravitational field, and it's that pressure that we feel. So the higher you get from sea level, the less that pressure is prominent. So that low pressure is here. Sorry, that atmospheric pressure is here, which is kind of like the normal distribution of pressure that you experience. Um, Now, when it comes to the compression phase, yes, it's this um, higher pressure. Now, at this particular point, um, these molecules are experiencing, this particular pressure, and their movement, their general movement has decreased. Their motion has decreased. Whereas if you look at the refraction phase, because there's such a there's less pressure than the other two phases, you can see that they're more spread out, and they got that ability to move around more um, during that low pressure phase. Now you can do a quick calculation here, where this value here is 101,302 pascals. If you do that over 1 centimeter squared, um, which is 0.0001, sorry, 0.0001 meters squared, you will get a value of 10 newtons, which is pressing all over your body at any particular time because of the atmospheric pressure. I digress. If we have a look at these diagrams, this is where the confusion comes up, because certain sources present them as particle displacements, which is they emulate how much movement the particles are experiencing by the nodes, and the antinodes represent the maximum motion that the particles can experience. So in an open pipe, um, the least amount of motion in the particles is experienced right in the center, and the most amount of motion is in the open ends of the pipe. Now, some texts present it the other way. They talk about pressure. They're both equivocal because they both add up, but they say that the crests or the antinodes tend to represent the pressure experienced within the pipe, which happens to be in the center, and the ends, the open ends, is the low pressure zone where the pressure is the minimum. They're both equivalent. They're just representing different quantities. One is dealing with pressure, and the other one's dealing with uh, the the quantity of motion of particles. Now, if you look at the closed pipe, it's the same thing. We mainly look at the fundamental frequency because if we understand this variance, then all the harmonics just fall in place as well. They just follow the same idea. So in a closed pipe, this is how I have emulated it, which is, um, the least amount of particle motion is happening at the closed end of the pipe, and at the open end of the pipe, you got the most particle motion happening. So all the gas molecules are in this low pressure phase. But when you observe that from the perspective of the pressure variation within the pipe, then you can see that the antinode region would be representing the maximum pressure that's experienced, and the node region will represent the least amount of pressure that is experienced. They're both equivalent, they're just expressing different phenomena that are occurring. So let's have a look at our closed pipe. So you can see with our closed pipe, this is the model I've used, and I've told you guys that a quarter of a wavelength in a closed pipe is equal to the fundamental frequency, and it's related to the length. So one quarter of the wavelength able to fit in that pipe is equal to the length of that pipe. Okay, and I've used the particle model where I'm saying that the particles have the least amount of motion at the closed end and the most amount of motion at the open end. Now this is equivocal with the pressure variation model. So here, rather than uh, being represented as a node in the closed end, which is represented as the maximum antinode phase that can be experienced by a transverse wave, and the closed and the open end tends to be the node where you have the least amount of pressure. And you can see they're equivalent sine waves, and they both say the same thing. They're just represented differently. They're still a quarter of a wavelength, but they still relate that quarter of a wavelength to the length of the pipe for the fundamental frequency. Now looking at the open pipe model, it's the same thing is occurring. I've used the particle model, so I'm saying that the particles are in the least amount of motion right in the center, and in the openings they are the greatest motion will be experienced there. But when you think of it from the perspective of pressure experienced in the pipe, well, then that antinode will represent a large amplitude, and those nodes will represent little amplitude, which indicates the low pressure regions in the open end. And you can see those sine waves are equivalent in terms of the quantity that they represent. Both of them represent half a sine wave. This one's more clear cut, whereas this one's a bit more confusing, but you can still see that they equal half a wavelength. And that's the general relationship that we get for the fundamental frequency of an open pipe, which is half of the fundamental wavelength that can exist in that pipe is going to be equal to its length.